In this section, we study our next kinematic variable, velocity. Although velocity will be important in its own right, it's mostly important because it is connected to position, because it is the rate of change of the particle's position. Like every other quantity, velocity has a symbol, in this case, v. Its units are meters per second. Velocity can be positive or negative, where in this case, the positive or negative signs indicate the direction it's traveling. So if we look at a number line like this one here, where say we have a cart confined to roll back and forth on a track, if it's moving in the positive direction, in this case to the right, then it has a positive velocity. If it's moving to the left, then it has a negative velocity. Again, that sign just tells you, is it moving in the positive direction or is it moving in the negative direction? Although generally referred to as velocity, the specific name of velocity is instantaneous velocity. This will be to distinguish it from average velocity, which we'll see in a minute. Instantaneous velocity will be most important because it will tell us the velocity of our object at any instant in time. And in this sense, you probably are familiar with measuring velocity. A speedometer in a car is essentially measuring velocity. It's telling you how fast you're going at any instant in time in the direction of travel. Let's look at an example. In this first example, we're graphing the same motion that we saw before, but this time we're graphing the velocity of that motion. So we first need to lay out our axes, put time on the horizontal axis with its units, and velocity on the vertical axis with its units. Now, for somebody standing still, they have no velocity, so our graph is pretty straightforward. It's just a straight line at 0 for 4 seconds. In part B, we're looking at a dog that's walking with a positive velocity for 3 seconds. And in this case, again, we need to draw our axes with time on the horizontal axis with its units and velocity on the vertical axis with its units. And because our velocity is constant at 2 meters per second, this is also a horizontal line at 2. In part C, we look at a cat that's walking in the negative direction with a negative velocity for 3 seconds. Again, we lay out our axes with time on the horizontal axis with its units and velocity on the vertical axis with its units. In this case, the velocity is constant, so it's just a straight horizontal line at negative 1.5. Some other quantities related to velocity include speed, which is the absolute value of velocity. So in the previous examples, the cat, for instance, was walking with a velocity of negative 1.5 meters per second, but its speed was 1.5. Average velocity, this is going to be the velocity over a whole course of a trip. We give it a symbol, v average, where average is in a subscript, and we typically read that as v sub average. The formula for average velocity connects what we think of when we think of average velocity, how far you traveled and how much time. And in this case, we can write it as the displacement over the time. While there is a single average velocity for the trip, there are infinite instantaneous velocities. So the instantaneous velocities will be most useful because it will tell us something at every point in time. Well, let's get some practice with average velocity. In this case, we're just looking at an average velocity of an object that moved from x equals 10 back to the origin in 5 seconds. Well, we first write down our formula for V average, the displacement over time. That's x final minus x initial over the time taken. In our case, the final position is the origin, so 0. The initial position was 10, and the time taken was 5 seconds. Simplifying that, we get negative 2 meters per second. And again, the negative sign makes sense here because we know that it was moving in the negative direction as it went from positive 10 back to 0. Here's another example that shows the difference between average velocity and what we would think of as speed. In this case, Carla drives to a friend's house, but then returns home. So Carla drove in a loop, and as we saw before, that means her displacement is 0. And if the displacement is 0, then the average velocity is also 0. Now this is very different than what the instantaneous velocity was doing at any point in time, or what the speed would be at points in various points in time. So it is important to understand the difference between these terms. Average velocity just corresponds to a whole trip, which in this case, her average velocity was 0 because there was no net movement throughout the course of the trip. Understanding how velocity connects to position is equally important. And what we'll see is that the velocity is actually the slope of the position versus time graph, so it is possible to read the velocity off the position versus time graph. In this example below, we see the position versus time graph of an elevator that starts from rest. What we want to do is look at this graph and be able to interpret what the velocity versus time graph looks like. So let's start by laying out our axes to match this. Time on the horizontal axis and velocity on the vertical axis, again, making sure to include our units. Now there are a couple important points on our position versus time graph which are worth paying attention to. The first is from 0 to 1 second. The next is from 1 to 3 seconds, then from 3 to 8 seconds, then from 8 to 9 seconds, and finally from 9 to 10 seconds. From 0 to 1 second and from 9 to 10 second, the elevator is stopped. We can tell this because its position is not moving, and so we know how to calculate its velocity. If it's not moving, its velocity is 0, so we can go ahead and fill that in on our graph. Now the next easiest motion to understand is from 3 to 8 seconds. In this case, the elevator is traveling at a constant speed, and we can tell that because we have a straight position versus time graph. We can calculate the speed of the elevator by using the idea of slope. In this case, our elevator looks like it starts at 4 meters at 3 seconds, and then it looks like it ends up at 24 meters at 8 seconds. Using our rise over run formula, we see that that leads to a slope of 4 meters per second. And again, that slope is the velocity, and so we can fill that in on our velocity versus time graph. Now, it's not totally clear what's happening from 1 to 3 seconds and from 8 to 9 seconds, but what we'll learn later is that the elevator is accelerating because of the curve in the position versus time graph. For our purposes, we'll just connect the lines from 1 second to 3 seconds with straight lines and assume it was accelerating at a constant rate. We'll discuss this more later. Similarly, from 8 to 9 seconds, we'll connect those with a straight line as well.